Good morning, myself Sri Lakshmi Madiraju. I am presenting my work Improved Session-Based Recommendation using Graph-based Item Embedding. So this is the outline of my presentation, introduction and my task session-based recommendation and the actual problem definition and the overview of the entire work, the major components, item embedding generation and recommendation framework, finally the experimental section and the conclusion. So firstly, what is a recommendation system? Recommendation system is a subclass of information filtering systems that seeks to predict user preferences over a given set of items, and they help us to find the interesting things to the user, and they serve as filters when the information is too much, huge information overload. And generally the recommendation is based on user interaction history such as user clicks, views, purchase, add to cart, etc. Whatever is the interaction. So it is based on user behavior. And item content such as features. The features can be discrete or numeric features, like for example consider a shirt, a fabric can be a feature, category, color, feet, sleeve, etc. These are the features. And the item description, etc. And it can be based on user profile and demography also, like age, gender, occupation, etc. So in our work, we consider the task of session-based recommendation, where users are anonymous and we only have user interactions organized as sessions. So what is a session? A session is nothing but a sequence of user interactions in a given interval of time. So we can think of a session as 1 hour or 1 week, whatever it is based on dataset and our specifications. So the user behavior in a given time interval is nothing but a session. So our objective is to leverage this limited data. So we only have user interactions. We do not have any user profile or item content, item features, etc. So we maximum utilize this data to produce good item representations and improve the quality of recommendations by utilizing these learned representations. So it has been shown that good user and item representations may improve the quality of recommendations. Since we do not have any user ID here, so we focus on item representations. So this is the problem definition. Let us consider I1, I2 and so on IM be the set of items, and S1, S2 and so on SN be the set of items, and each session can be represented as a sequence of interactions where xit is the item interacted at time step t in a given session Si, and given all session sequences and a target session with some user interactions, the task is to predict the next possible interaction. This is our problem. So let me give the overview of my work. We have two independent modules here. The first module is item embedding generation and the second module is recommendation framework. In item embedding generation, we create a heterogeneous graph, which is a bipartite graph of sessions and items, and we learn the embeddings for items using the method called transhe. So the details I will present in the next slide. And the second component is recommendation system. So once the embeddings are learned, we use those embeddings, like those representations, in the recommendation framework. We use a standard LSTM with attention framework for next item recommendation. There are these 4 layers: the input layer, where the items are represented with the graph embedding learned in the first stage, and the LSTM layer, and there is an attention layer, and the final output layer. So we will discuss this framework in the next slides. This is the overview. So in item embedding generation, we create a graph in which all items are nodes and all sessions are nodes. Items in the sense item IDs and session IDs are nodes. And 2 items are connected through the session in which they co-occur. The edges are based on the co-occurrence of these items, and 2 items are connected through the session in which they co-occur, and the direction of the edge, the graph is directed, and the direction of the edge is based on the order of the occurrence of items in the session. So if I1 and I2 are occurred in the order, then the edge is from I1 to I2 through the session S in which they co-occur. So yeah, then we generate the triplets in the form E1, S, E2, where E1 and E2 are item entities and S is the session entity through which they are connected. Then we apply the method called transhe, which is a very standard knowledge graph embedding, and we have chosen this method since it is very simple, very effective, and the complexity is less, and it is shown to capture multiple relations very effectively. Now, yeah, this is the graph. Let us take three sessions, S1, S2, S3, and S1 contains I4, I2, S2 contains I4, I5, S3 contains I2, I8 and I5. So we create the graph based on like all sessions are nodes and all items are nodes, and the edges are like I4 is connected to I2 through S1, similarly for others, and we generate the triplets accordingly. Now what is transhe? So given a triplet, we obtain the triplets from the graph. Given a triplet E1, S, E2, the relation S is interpreted as a translation vector so that E1 plus S equals to E2 in the obtained space. Like that is E1 hash plus S hash is approximately equal to E2 hash with a minimal error. So approximately equal to E2 hash. So the algorithm is, let us take the training set T equals to E1 S E2. E1 or E2 are entities and S is the relation. So in our case E1 and E2 are items and S is the session. So and there is a margin. We are using the margin loss gamma and the embedding dimension is D. So we initialize all our entities to a random vectors and at each iteration we normalize the embeddings. Then we sample few triplets from the training set to get the batch input, and for each triplet we corrupt the triplet. So how do we generate the corrupted triplets? We can replace the head entity or tail entity by some random entity to obtain the corrupted triplet for that triplet. So we add this set of corrupted triplets to the batch and the training batch, T batch. Then we update the embeddings with respect to the following loss function. So where D is the distance matrix, it can be L1 or L2 norm, and gamma is the margin, and E1 and E2 are our entities and S is the session. So yeah, so the difference between the positive triplet and negative triplet is maximized. So once we obtain the embeddings, we utilize them for the recommendation. So this is the sequence V1i, V2i, Vt minus 1i and Vti. Each item is denoted with the graph-based embedding and we input them to the LSTM layer, and a hidden state is computed by using the previous hidden state and the current input, and then we apply attention on top of that to give more weight to the items which are more relevant in the prediction. We know that all the items do not contribute equally to the prediction, so the items which are more relevant are weighted more using attention. So M is the weighted sum of these hidden states, and M is given to a dense layer. The number of units in the dense layer is equals to the total items or total vocabulary, and the activation is softmax, and we obtain the probabilities of all items. So we rank them based on the probabilities and we recommend the top item to the user. Now the experimental section. So we evaluated our model on two different data sets. One is UChoose, which was released by Rexis 15 challenge, and it consists of 6 months of clickstream data. And the second is Designetica, which was obtained from CIKM Cup 2016, where only its transactional data is used. And according to the previous literature in session-based recommendation, we remove the sessions of length 1 and items that appear less than 5 times. So these are the data statistics after pre-processing. Now the evaluation metrics. We use recall and MRR, both are at the rate 20 to evaluate our model. So recall is nothing but the proportion of cases where the actual item is among the top K predicted items, like top 20 here. And MRR is the mean of the reciprocal ranks of correctly classified items. And if the actual item is not in the top k, then the rank is considered as 0. And the experimental setup, the item embedding dimension is 100 and LR is 0.001, and we use Adam optimizer, and the batch size is 512, and there is a dropout of 25% between LSTM and attention, and we used only one LSTM layer, and the number of hidden units is 100. And we compare our model with graph-based embedding, again a standard prod-to-vec embedding and the combination of both. So what is this prod-to-vec embedding? This is a standard embedding which is similar to word-to-vec in NLP. So it finds a d-dimensional embedding for all items such that the items which co-occur together in a window, in our case a window is a session, are closing the resulting vector space. So it learned the embeddings by minimizing the weighted cross entropy between the empirical and the modeled conditional distributions of context items given the target items. So you can see in this picture, ik is the context item, target item, and ik minus 1 and ik plus 1 are the context items. So we predict ik minus 1 and ik plus 1 from ik. So we compare our graph-based embedding with this prod-to-vec embedding and the concatenation of both embeddings. And the final results of our recommendation framework, we compare with the following session-based baselines. So the traditional recommendation methods such as popular, session popular, item KNN, and Bayesian personalized ranking and Markov chains, etc. And most popular methods for SRS, those are RNN based methods, that is GRU for rec, and the combination of RNN and attention methods like STAMP and NARM and SRGNN, which is the state-of-the-art method. And we also want to show that the embedding can be incorporated in other recommendation frameworks also. Like since these two are independent modules, we can incorporate this embedding in any other recommendation framework and make it effective. That also we show with NARM method in our work. So yeah, NARE is our method and NARM is the state-of-the-art method for SRS, and these are the traditional methods, popular and S popular, etc. So obviously the neural based methods outperform the traditional methods, and SRGNN is the state-of-the-art method. So we show that the graph-based method embedding is better than prod-to-vec embedding in both you choose and disanalytical datasets, and the combination is better than both because the combination captures two perspectives, like prod-to-vec embedding captures the sequentiality among the items and the graph embedding captures the co-occurrence across the sessions. So the combination of both captures both perspectives, so it performs much better than either of these. So we show that NARM with our embedding performs better than standard NARM, and we got the state-of-the-art result on UChoose dataset with the NARE combination and on Disanalytica with NARM combined embedding. So let me conclude. We show that graph-based embeddings perform better than the standard prod-to-vec embedding and also achieve state-of-the-art results. And the reason is the learned graph-based embedding capture more implicit connection between the items, which helps to improve the quality of recommendation. And we also show that these embeddings can be used with other recommendation frameworks also. And we have demonstrated this by incorporating our embeddings as input to NARM. This can be given to any other recommendation framework. So thank you. If you have any queries or any suggestions, kindly let me know.